Welcome back to the Open Foam tutorials of the University of Birmingham. In this tutorial I will show you how to increase the mesh resolution of the cavity case. In this tutorial, the mesh resolution will be increased to improve the quality of the simulations. The mesh resolution will be increased from 20 cells in the X and Y direction to 40 cells. First, a CavityFine directory will be created. The CavityFine case will be very similar to the cavity case, so we will copy the constant and system directories. Now, we will navigate to the block mesh dictionary. To increase the mesh size, the block mesh dict file need to be changed. The number of cells need to be increased from 20 to 40. I will go back to the home directory. Inside the polymesh directory, the old mesh still exists. To rewrite the mesh, I will run the block mesh application. The application will rewrite the mesh. It is possible to copy across the 0 directory from the cavity case, and run the simulation again. However, the simulation runs much quicker if the results from the course mesh are mapped to the new mesh. This is done by using the map fields utility. The field data that map fields maps is read from the time directory specified by start from and start time in the control dict of the target case. Here we wish to map the external results of the coarser mesh from case cavity onto the finer mesh of case CavityFine. Therefore we first need to change the control dict directory. Since the results are stored in the 0.5 directory of cavity, the start time should be set to 0.5 in the control dict dictionary. A description of how to use the map fields command is given by typing in help. It should be noted that the help option can be used with any utility and information detailing this application will be provided. Since the source and target geometry and boundary conditions of the case are identical, the consistent option should be included. Now, the map fields utility will be used. You can notice that a new time directory named 0.5 is created in the CavityFine directory. The end time of the simulation should be set to 1 second. To ensure that the Coulomb number remains below 1, the time step should be reduced. Since the cell size has been halved, the new time step delta t should be set to 0.0025 seconds. The write control option can be changed from time step to run time. Since the write control has been changed to run time, the write interval should be changed to 0.1 seconds. The case will now be run with the icofoam application and the output saved into a logrun file. We will now have a look at the contents of the logrun file. For each time step, the quorum number and the residuals are reported. The simulation has been started from time step 0.5 seconds. You can see that the final time step is at 1 second. The residuals can be plotted in a native Linux plotting program, gnuplot. In able to do so, we need to copy a text file. I will copy the file named plotresiduals.txt from my own machine and place it in the CavityFine directory. The residuals.txt contains information about what data will be plotted. It will automatically update the figure every 100 seconds. The residuals can be plotted with gnuplot. As you can see, the residuals are decreasing to 1, e to the -6. The results are post-processed in Insight. A clip plane, colored by the velocity, of the two different mesh sizes are shown. It could be seen that the mesh size has an influence on the results of the simulations. Thank you for watching. In this tutorial I have shown you how to increase the mesh resolution. The next OpenFOAM tutorial will focus on multi-phase flow.